Yes. So hello guys. In this session, we will start ISRO 2020 mechanical engineering solutions. In this, we will try to solve strength of material and machine design.
Sir, 2018 have we done?
Yes, sir, we have done. Last session was on 2018 only.
So 2017 also we have done because there are two
So
20.
15, 16, 17, two sets, and 18
Okay,
we
done.
have done.
Yeah, okay, done. Thank you, sir.
Yes. So here we will try to see first question. That is machine design question. In a screw jack, first of all, see read the problem. This is also most frequently asked question in many examinations. So ISRO also tested the knowledge of screw jack and whether we know the turning moment and the load required to lift uh, any load by the screw jack or lower the load by the screw jack. So we will try to go through a complete explanation of screw jack and the lifting and lowering the load with the help of this instrument. Okay. So very first of all, note down screw jack, and we will try to go through the basic of screw jack. Okay, so here, so when I basically show you the diagram of screw jack, how the lifting will happen. So there is a stand. So this is a very rough diagram I am making here, and why? Because I not only want to discuss this question, but other question also I want to discuss, which they already asked in other examination based on this screw jack. So this is the nut, and here we have the screw with the thread profile, and here we have the cup through which we are applying the basically load to lower any or to lift any kind of or any amount of load. That's why for ISRO examination, I must say thread is very important. All the types of thread and their important things related to the threads like acme, trapezoidal, and square threads. Try to read from the VB Bhandari. That is the best source you can get. If any question will be out of the range of VB Bhandari, that mostly will not be able to answer by most of the candidates because they will not be given in any other sources, right? If you want to follow, you can follow Sigle, but I will not recommend you because that is a time consuming, especially for one subject. If you go for two, three books. So this is the nut we have, and this is the basically a screw thread we have. So this is the basically jack. Here we are applying the load so that with the help of this L, we are basically applying movement, turning movement, so that we can lower or we can lift any amount of load. In this one, our focus would be on this screw thread profile, right? Especially when I talk about screw thread profile. So here you can see here there will be core diameter, mean diameter, and D, that is the nominal diameter. Nominal diameter, core diameter, and then we have mean diameter. mean diameter. Here you try to understand the diagram which I have drawn onto the right side of this. So there is a basically this particular diagram they have given, right? The load, whichever the load we want to lift it, that is a load which will be given to you, W. Alpha is a helix angle. We also call lead angle in case of screw threads. In case of screw threads. Now, whatever the load we are applying, see that we are applying the load perpendicular to the weight which are acting. The weight is acting in the downward. We are applying the load tangentially, right? So that we can lift it. So that we can lift it. Now, if you want to calculate how much amount of load required to lift by using this screw jack, then what will be the free body diagram? The free body diagram will be what? Note down the next topic. Here, whatever the diagram you have seen, you keep it in your mind, whatever the diagram which we have drawn, because if we multiply with this Rm, you will be getting torque, that is P into Rm. You can also write P into dm by 2, mean diameter by 2. That is a torque which is required to lift it. Now the direction of P, again remember, P is an imaginary load. P is a imaginary load in this case. We are totally focusing our attention on this particular segment. This particular segment, whatever the segment you are observing with the red color, we are focusing our attention on this red segment. That is a screw thread profile, and we are assuming that whatever the load, actually we are applying the load is what F, right? But we are trying to saying that we are applying the virtual amount of load or imaginary load on the screw thread at a mean radius, at mean radius, not core diameter, not at the outer diameter or nominal diameter. We also call this to be outer diameter. We are applying the imaginary load at the mean radius or mean diameter, right? So now you should be focusing that actually P we are not applying. We are just doing for our analysis purpose, right? Now we have to calculate P in terms of W, and that is what they have asked in this particular question. How much amount of effort will be required to lift the load W will be how much? Phi is a friction angle, lead angle or helix angle they have given as alpha, right? So here what we can make the free body diagram of thread profile. Here this is a inclination of thread profile which is there at an angle what, alpha, and there is a load which is being, whatever the load is there, that this is the load, right? We want to lift it. The load W will be acting in this direction. We are calling this to be load W mg. Now my dear friend, when we want to the load required or effort required to lift it, effort to lift the weight, how much of effort will be required to lift it when the any amount of load will be lifting in the upward directions, right? In this particular direction we are lifting in these directions, then in which particular direction my friction will be acting? My friction will be acting in these opposite directions, mu into n, where n is what, normal reaction force. And how much of actually imaginary effort we are applying? We are applying the effort P in this direction. Why we are applying in this direction? Here we are applying the P towards the right to overcome the friction, right? P is acting towards the right to overcome the friction, and rise the load. See, then only the component of P will be acting in this direction, right? That is a P cos alpha, and this will be the what we call P sin alpha. So actually we are trying to doing is that P cos alpha will help to rise the load, right? Because it is acting in the upward directions, right, in the upward direction, whereas friction is acting in the downward direction. So definitely it will help to rise the particular load, right? So these are the segment we have normal reaction force, which will be acting like this. Mu n will be acting in the downward directions. That is what the load we need to lift it. Now, how much of travel will be there for the load W? The load W initially will be here, and then it will be lifted up to this much height. From the starting lower position, it will be lifted from A point to C point, whereas we have drawn at somewhere at the middle or maybe somewhere in between A and C. We want to transfer the load or rise the load from A point to C point. Okay. While doing so, if you draw the free body diagram and resolve the forces, right, then definitely summation of forces in the horizontal direction should be 0. Do that. You resolve everything in the horizontal direction. So I'm just removing this resolutions. See, that is a p cos alpha. Here, that is a p cos alpha, and perpendicular to this will be p sin alpha. Right. Earlier, I have drawn incorrect the basically direction of vertical load. That should be perpendicular to that p cos alpha. Now summation of forces in the x direction. So p minus, what should I write? Now what about this? This will also be alpha, right? Whatever the mu1 is acting, mu1 is acting like this. What is the angle alpha? So this component will be what? Mu1 cos alpha. This component will be what? Mu1 sin alpha, right? So here you can write mu1 cos alpha. What about the normal component? Normal component is acting like this. What about the angle? This is alpha. This will be alpha. This will be 90 minus alpha. So what about this component? This will be n sin alpha, and this will be n cos alpha. So this will be acting minus n sin alpha. That is equal to 0. So what about p? P will be mu n into cos alpha plus n sin alpha. That is the first equation. Note down. That is what we have the first equation. What about the second equation? What about the second equation? Summation of forces in the y direction, that has to be 0. What is acting in the vertically downward directions or in the y direction? W and normal component and this friction force, right? There will not be any component of P in the vertical downward, right? Because we are assuming this to be X, this to be Y. So here what we can write is that W, that is equal to n cos alpha, because n cos alpha and this mu n sin alpha, will be acting in the same direction of W, but n cos alpha is acting in the opposite direction of W, right? So here we can write the n cos alpha plus mu n sin alpha. So W we can write n cos alpha minus mu n sin alpha. So this is our second equation. This is what we have our second equation. Now divide and basically you divide equation 1 by equation 2. Equation 1 by equation 2. So here what you can get, P is equal to what? P by W, that you can get mu n cos alpha plus n sin alpha divided by n cos alpha minus mu n sin alpha. Now what you have to do, you can take n as common, right? And you can just take it this side, mu cos alpha plus sin alpha divided by cos alpha minus mu sin alpha. Further P we can write W. What we can write? We can write here it as we can divide numerator and denominator by cos alpha. If we just divide by cos alpha, what I can get? I will be getting here. I'm writing here. P we can write W. We can write mu plus tan alpha divided by 1 minus mu tan alpha. What is a mu? Mu, we know that is tan phi, where phi is what? Friction angle. So from here, what you can write? P is equal to W into tan phi plus tan alpha divided by 1 minus tan phi tan alpha. All together, what we can write, my dear friend? We can write this as, we can write this thing as P is equal to W tan phi plus alpha, because tan A plus B, we know the formula tan A tan B, tan A plus tan B divided by 1 minus tan A tan B, right? Make a note of it. Please note down, it is very, very important. I am doing the derivation just not for the SOP's purpose. You have to note down, because again I am repeating you, do not completely uh, basically carry on your preparation just based on the previous year questions. Whenever you see any question, screw jack, you try to read everything related to screw jack, because they might be interested and they will be giving you this year question also based on screw jack. But that may not be the same. They can ask the effort required to lower the load W. Again, I'm repeating, and today also I'm repeating the same thing. So this is what the effort, we got the answer, right? This is what the effort will be required to rise the load W. Now you can see it is depending on phi as well as alpha. Now in the same particular question, if I'll be asking you how much of torque will be required to basically rise the load W. See, if you want the answer, we got the answer, right? We got the simply answer B, but that is not our purpose of doing this session. Uh, Here note down the torque M required to rise the load W. Torque, you know that what is the value of the torque? That is effort P into mean radius. M will be what? P into dm by 2. We can further write M is equal to what? W and phi plus alpha into dm by 2. That is the M required. Note down. Note down the next topic. Effort required to lower the load W. If you just draw the diagram, what you will find, this is the lead. Remember, this is the lead L. Your load will be lifted from A position to C position. How much of height it traveled? It traveled the height lead L, right? So now if you draw the free body diagram, what you can make? W load. Now if you want to lower the load, if you're lowering the load from C to A, the friction will be acting like this in the upward directions. And the effort will be required in the opposite direction of what? Lift. Opposite direction of the what we call coefficient of friction, that is P. Whatever the friction force is acting, P will be required in the opposite direction of mu n, but tangentially, right? Tangentially. Do not draw the P value like this. Don't say P value like this, because I shown basically in the diagram I have shown you that it will be acting perpendicular to the load W. You can see, if you have still any doubt, you can see the load P is perpendicular to the load W. The load W is acting like this, your P is acting like this. Both are perpendicular to each other. Now, if you just resolve the forces, summation of forces in x direction to be 0, summation of forces in the y direction to be 0, if you just do these two things together, you will get the final formula. And the final formula, that is effort required to lower the load W, will be what? P is equal to W then phi minus alpha. Again, the question they have not asked about the lowering the load, but I am discussing because further consequences are there regarding this particular formula. Note on, then I will tell. Now how much of movement will be required? Movement will be P into dm by 2, that is W into tan pi minus alpha into dm by 2. No doubt. Now what you are understanding by this formula? The torque required to lower the load. The torque required to lower the load is what? W into tan pi minus alpha, pi minus alpha into dm by 2. If, my dear friend, phi will be less than alpha, phi will be less than alpha, the torque required to lower the load will be negative. Then M will be what? Negative. M will be negative. It indicates that you do not require any force. You do not, literally, you do not require any movement, any load to lower the load. The load itself will begin its motion in the downward direction without your permission. That means, suppose in a car mechanism, right, in a car soft floor, you are doing some car repairing work, and you have lifted the car up to certain height, and you are doing some work. Suddenly what happens, that your car is lowering down without observing, no without your permission. You have not applied any movement to lower the load, but automatically it is giving its motion in the downward direction, and that is a very disaster. Any accident can happen. This condition we call overhauling conditions. Overhauling conditions, right? So down. It indicates, it means no force required, no force required to lower, no force required to lower the load. The load itself, the load itself will begin to turn down, will begin to turn down. This condition we call overhauling condition. And for any screw thread design, for screw jack, it is not at all advisable conditions, right? This is not a very favorable conditions, right? This is also called back driving of screw, right? So this is not useful in screw jack application, right? Make a note of it. That is the first. Second thing, second point, when phi is more than or equal to alpha, when phi is more than or equal to alpha, then a positive torque will be required. Then at least a positive torque will be required, right? And the whatever the load is there, it will not automatically turn down. It will not be ascending, descending down, right? It will not be starting its motion without your permissions. When you just give the permission, when you just apply the movement, then only it will be coming in the downward directions, right? So this condition is called self-locking conditions. So some of the examinations, basically they have asked that for self-locking condition, what is the criteria? Whether friction angle should be more than or equal to helix angle should be more than or equal to friction angle, all those things, right? A self-locking screw will hold the load in a place without a break, right? So 10 phi will be more than 10 alpha because phi is more than alpha. So we can write mu is what? Greater than L divided by lead divided by pi dm. Because when you see the diagram here, when you see the right angle triangle, this triangle, this is what we have lead, this is what you have pi dm. When you open the thread, you will get pi dm perimeter, and this is what we have alpha. So tan alpha is what? Lead divided by pi dm. Lead divided by pi dm. So for the self-locking, there should be sufficient friction. If the friction will be low, if the friction will be low, there cannot be self-locking. There cannot be self-locking. Now, note on the last point regarding this particular screw jack. Efficiency of square threaded screw. What is the efficiency actually? Right? Note on the efficiency. Work output divided by work input. How much of work output we are expecting? We are expecting to traverse the load from A point to C point. That means W into lead. That is what our expectation is, my dear friend. And how much of work input we are giving? We are giving the work input P into, that is of effort. How much of effort we are doing? That is P into pi dm. P into pi dm. Now here we can write W divided by P. Lead divided by pi dm. Lead divided by pi dm. Pi dm. We know that this is tan alpha. So efficiency we can write tan alpha into W by P. P effort to basically rise the load will be how much? W into tan alpha plus phi. So put down the values. We can write here tan alpha divided by tan phi plus alpha. No doubt. So your efficiency is depending on when you see very carefully, your efficiency is depending on alpha phi. Now alpha is depending on what? Lead and mean diameter. Mean diameter, right? So in short, efficiency is depending on what? Efficiency is depending on mean diameter of the screw, lead of the screw, and coefficient of friction. And coefficient of friction. When this efficiency will be maximum? When this particular efficiency will be maximum? There is a certain mathematical procedure. I'm not doing that mathematical procedure. You just note down for maximum efficiency of, here only you can make a note and you can note down for maximum efficiency of square threaded, this thread. I'm not talking, and we are not having any discussion regarding Acme or other trapezoidal threads. I'm talking about square thread. Efficiency, maximum efficiency will be there when 2 alpha plus phi will be equal to 90 degree. Or we can write alpha is what? 45 minus 5 by 2. Note down, when alpha is equal to 45 minus 5 by 2. Now when you put maximum efficiency, that is 2 alpha plus phi, that is 90 degree, you will get 1 minus sine phi divided by 1 plus sine phi of maximum efficiency of square threaded screw threads. So this particular formula, this condition you have to remember, and this particular formula for maximum efficiency. So these are the things they have asked in other examination also. So don't have actually, if you are expecting from ISRO that they will frame a new question, no, they don't have time. So definitely they will do copy paste. But question, whatever the question they will keep it, that is of somewhat of quality level, right? That is my prediction. It can happen anything. They might be given below average paper also, just like what we have seen in way back 2012 or 11, right? So these are the things we have to discuss. So what are all the things we have discussed? We have discussed what is the purpose of this screw jack, and then how much of load will be required or effort will be required to uh, lift the weight, whatever the load is there, and then we have seen the how much of effort will be required to lower the load or to lower the weight, and then we have seen some condition overhauling conditions, and then self-locking conditions, and then we have discussed efficiency of square threaded screw. Okay. Note down the second question and try to observe. So already we have discussed. If you can answer, try to answer this question. Question number 57. So we have seen that in case of rectangular section, when your rectangular section is subjected to shear force, then we have seen that there will be parabolic variation of shear stress. That is maximum at the neutral axis, but zero at the top and bottom fiber. So they are asking what is the relationship between average shear stress and this is the maximum shear stress. How to get the value of maximum shear stress? Maximum shear stress we are getting at the neutral axis. And what is the actual formula? Shear force into A into y bar I multiplied by B. Let's say B is the diameter, B is the width, and D is the what? Depth of particular section. Neutral axis will be at the centroid. This is a particular section which I am hatching. Right. Now, if you try to calculate the values of centroid of this hatched portion, that will be my y bar, and area of the hatched portion will be what? B into d by 2. What is the y bar? Y bar is what? D by 4. Then I is what? BDQ by 12 into B. When you do that, you will be getting 3 by 2 F divided by B into D. Average shear stress, we know that F divided by BD. So whatever the maximum shear stress should be there, 3 by 2 times of tau average. So 3 by 2, that is C option is correct. Make a note of it. That is a very important. Note down for other section also. Note down for other section also. Tau max will be K times of tau average, where K is 3 by 2 for square section, rectangular section, and triangular section. K value is 4 by 3 for solid circular cross section. K value is 9 by 8 for diamond section. When the diagonals are rotated, by 45 degree of square section, then we can get diamond section. This particular diamond section, we have K value 9 by 8. So for the square section also you will get the same thing. When they talked about the series stress, I'm giving you as a homework, you try to answer. In the next particular session, I will try to answer this question. This particular T section we have, which is having a width B, T, T. Again, we let's say here it is B. And suppose four options are given to you. Which of the following you need to answer? A, B, C, and none of the above will be D. The confusion might be between A and B, right? Actually, I want to ask you where exactly, let's say here we have the neutral axis. Whether at the neutral axis you have maximum shear stress or at the junction of flange and web section. So you please try it, right? Try to see the values and compare the value at the junction A and let's say neutral axis B point. You try as a homework. Here Tom X. Here we are getting Tom X. Now moving on to the next question. Question number 58. Again, the massless beam. Massless beam means we need not to consider any the weight of the beam. Has a loading pattern shown in the figure. Find the bending moment at the mid span. That means bending moment at the B point. So again, we will try to see this question. So I'm basically drawing once again in our next page, and we will try to draw the bending moment diagram also. This is the point A. This is the point B, point C. Here that is 4 kilonewton per meter. Here the reaction force RA. Now you understand there is a load W which they have given. So first of all, find the bending moment when you start from left to right, for example. Then what is the bending moment at A? That is 0. Bending moment at B. So that is RA. First of all, what is the RA and RC value? Then for this we have to calculate. So summation of forces in the y direction to be 0. So RA plus RC, that is 4 into 1. That is 4. Summation of moment about A point to be 0. Then 4 into 1 into 0.5. RC into 2. RC will be 1. What you will get RC? RC you can get it as 1 kilonewton. Then what about RA? RA will be 3. So what about the bending moment? Bending moment at B point will be RA. RA is what? 3 into 1. That is a sagging bending moment. Minus, why minus? Because of uniformly distributed load, there will be hogging bending moment of 4 into 1 into 0.5. Because this will be acted like this at the midpoint of 1.5 meter. 3 minus 2, that is 1 kilonewton meter. What about the bending moment at C? Again 0. So what is the bending moment at B point? That is 1 kilonewton meter. That should be the answer. So what is the answer? A. Now if you draw the bending moment diagram, how you can draw? This is point A, point B, point C. Bending moment between A and B. For a uniformly distributed load, your shear force variations will be how much? Because we know that W is what? Minus of dF by dx, and F is what? Dm by dx. right? So what we can write here? Slope of the shear force diagram, whatever the slope of the shear force diagram is there, that will be constant. That will be constant or variations, having some variations. Let's draw the shear force diagram also. So what you can get from here, shear force at a point will be upward or downward. According to our standard sign convention, when we follow like this, so that is our plus shear force. So that is plus. Shear force at B will be what? How much of shear force you can get at B point? That is RA. R is what? 3 minus 4 into 1. So that is minus 1. So you can get here minus 1. But we have to draw it by certain diagram like this. Again at C we have 1, but there is a constant. So this will be my shear force diagram. So what you are understanding, what is the value of shear force somewhere here? Somewhere here, let's say D point, you are getting the shear force to be 0. Where exactly you are getting the shear force to be 0? Let's calculate. Let's calculate. Shear force at any section you first consider that is to be 0. At any section XX from A, you just consider any section, right, at a distance X. So RA is what? 3 minus 4 into X, that is 0. So X will be 0.75 meter. At a distance 0.75 meter, you are getting the bending moment, shear force to be 0. So there the bending moment should be maximum, right? So you calculate the bending moment at D point also. So RA, that is 3 into 0.75 minus 4 into 0.75 into 0.75 divided by 2. So how much of value you are getting? 3 into 0.75 minus 2 into 0.75 into 0.75. So you will be getting 1.125. So in the same problem, if they would have asked the maximum value of the bending moment, that one is not correct. 1.125 should have been correct. So now you can see the shear force is what? Decreasing. The slope of the bending moment diagram should decrease from A to D. From A to D, slope of the bending moment diagram should decrease. How we can draw the decreasing slope? Like this. Now, what is happening between D to B? D to B, the shear force is actually increasing. When shear force will increase, so slope of the bending moment diagram should actually increase. How the slope will increase? Slope will increase like this. The slope will increase like this. Here to here, the value is what? 1.125 kilonewton meter. That is D point. And at B point, we know that the value is what? At particular B point, the value is 1 kilonewton meter. And what about the value between B and C? Of course, shear force is 0. The bending moment diagram should be 0. From here to here, we should join by straight line. So from here to here, that is a parabola. And this line should be 1 degree. This both the lines should be of 2 degree. Make a note of it. This will be your shear force diagram. This will be your bending moment diagram. This is an increasing slope, right? Slope is actually increasing. This is what you have, decreasing slope. Slope is maximum, getting 0, 0, flatten. Again, it is increasing. Now, we'll try to solve the next question. That is the 59th question. Now, again, same problem we have discussed regarding ISRO 2018 paper also. The von Mises stress. What is the von Mises equivalent stress? That is yield stress divided by factor of safety. that I told you the complete formula. If you can recall the complete formula, half of, can you just tell the formula? Half of sigma 1 minus sigma 2 whole square, half of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. That is the actual formula we do have regarding the von Mises stress. But here they have given sigma 1 300, that is also equal to sigma 2, sigma 3, that is 0. Biaxial means what? Sigma 3 automatically 0, sigma 3 0, sigma 3 0. So sigma equivalent, what you can get? Half of sigma 1 minus sigma 2, that is 0 square, plus sigma 2 square plus sigma 1 square, that is 2 sigma 1 square. So finally answer will be sigma equal to sigma 1. Sigma equivalent will be 300 megapascal. D should be correct. So from 2018 to 2020, again they have repeated a very similar question, right? It's a very common and human nature, right? We cannot frame the question new every time. So definitely they will do the copy paste, but little bit changes in the data. So now you know the wound mices is very important. So after 2020, we have paper this time 2023. So definitely the question might be there on wound mices. Not exactly the same von Mises stress, but they can ask any other question based on this von Mises. Either the graphical things or some theoretical question to compare the factor of safety component as compared to maximum shear stress theory or Tresca's theory. Even after knowing ISRO has repeated 2 times von Mises, even though you are ignoring this topic and going in the examination hall, which will happen in next month, without knowing the von Mises, that is a very blunder mistake. Now, try to solve the question number 61. A cylindrical pressure vessel has a diameter 200 mm. The diameter what they have given 200 mm. Thickness they have given 2 mm. They are asking what is the hoop stress. Like if you take any component, there will be hoop stress. There will be longitudinal stress. There will be longitudinal stress. When it is subjected to the pressure of 5 megapascal, what is the value of hoop stress and longitudinal stress? Right? That is what we need to answer. So try to answer. All of you might be knowing the formula. Okay, now when you try to see this question, they are asking what is the hoop stress and what is the longitudinal stress. So hoop stress, we know the formula. When you consider hoop stress, we know that is PT divided by 2T, and the longitudinal stress will be Longitudinal stress or axial stress will be PD divided by 40. So P is what? 5. Diameter, internal diameter is what? 200 mm. 2 into T. What is T? 2. So now when you calculate hoop stress, you will be getting 1000 divided by 4, that is 250 megapascal. Longitudinal stress will be 125 megapascal. So answer D should be correct. Now try to see the next question. For a long cylinder column, of uniform cross sections, the ratio of critical buckling load for the case with both the ends are hinged. Whereas both the ends are clamped. Right. In both the cases, we have to determine the ratio of the buckling load P1 to P2. So what is the formula for here effective length alpha? Here alpha will be what? 1 upon 2. Here alpha will be 1. So P1 we know that pi square EI divided by what? Alpha square L square. L is same, E is same, I is same. So we know that P will be what? Inversely proportional to alpha square directly. So P1 divided by P2 will be alpha 2 divided by alpha 1 whole square. Alpha 2 is what? 1 upon 2 whole square. So that is 1 upon 4. 1 upon 4 will be 0.25. He will be correct. Make a note of it. And the fixity coefficient you have to remember alpha 1 upon 2, 1, 2. I told you the shortcut, right? 1 upon 2, 1 by root 2, 1, 2. Both the ends fixed free, fixed pin, and then we have fixed free. Now moving on to the next question. If the length of the column, subjected to compressive load is increased by 3 times than the original length, L2 will become 3 times the original length. Then what about the critical load? Just now I have given the formula pi square EI minimum divided by L square alpha square. So P critical will be what? Inversely proportional to L square. The larger and larger amount of load, the larger and larger amount of length of the rod, very easy to buckle it. Very easy to buckle it. Little bit amount of load, it will buckle. Right? So what will be P2 by P1? That is L2, sorry, P2 by P1 will be L1 by L2 whole square. L1 by L2 whole square. L1 by L2 we know 1 upon 3 whole square. So that is 1 by 9. That is C should be correct. Note down. Now, moving on to the next question, question number 64, and we will try to see the square bar of size 10 by 10 mm and the length is 1000 mm is subjected to 200 Newton axial tensile force. The bar is made up of still having a modulus of elasticity 200 gigapascal. Find the strain energy density. What is the meaning of strain energy density? Is strain energy per unit volume. That means half of stress into strain. That is the value of basically Newton mm per mm cube. Strain energy per unit volume. That is called as strain energy density UD. Now we know that stress is what directly proportional to strain E times of strain. So strain will be what sigma by E. So here we can write sigma square divided by 2E. Now I have told you the unit, so you need to be think accordingly. Sigma, what is the sigma? Load divided by area whole square divided by 2. What is the load? Load we know 200 Newton. Area we know 10 into 10 whole square divided by 2 into 200 into 1000. And what is the unit? Just now I have given Newton per mm square because 1 mm will cancel out. This will be the unit. Now, again be careful and try to tell me the final answer in that unit, that is Newton mm per mm cube. So 200 divided by 100 whole square divided by 2 divided by 200 divided by 1000. So now when you do that, you will be getting 1 into 10 to the power minus 5 Newton mm per mm cube. So now the game for this question is unit. You have to be very careful about the unit. That is a joule. 1 joule we know that 1 Newton meter. So that will be again divided by 1000. So that is a Newton meter divided by mm cube. Again they are asking in joule per meter cube. So what we can write 10 power minus 8 divided by 10 power minus 9 joule per meter cube. So what should be the answer then? 10. A should be correct. When you convert mm in meter, 1 mm is what? 10 power minus 3 meter cube. Uh, that is 1 mm is what? 1 mm is 10 power minus 3 meter. When you do the cube, it will be cube, right? So that will become 10 power minus 9 meter cube. That's how in the denominator we have 10 to the power minus 9. 1 gigapascal, 1000 megapascal. We also call this term to be modulus of resilience, right? Modulus of resilience. Now moving on to the next question. A solid circular shaft need to be designed. Now you can see every year we have in this row this particular the question based on the uh, torque, right? Or transmission of the shaft. So this is very important thing, right? Only the thing is that we have to be very careful about the uh, what we call calculations, right? So what, we know that tau is what 16 t divided by pi d cube, tau max. Now tau max is what 280. That is 16t. What is the torque that we need to calculate? No, that is given 55 Newton meter. 55 Newton, that will become what? Newton mm, right? 55, when you do multiply with 1000, it will be Newton mm divided by pi d cube. So here, when you do the solution, d will be what? 16 into 55 into 1000. divided by pi divided by 280 to the power 1 upon 3. So now when you do the calculation, you will be getting here pi you need to put 22 by 7. What you need to put 22 by 7? Here 22 by 7. So when you do that, you will be getting 10 mm. B should be correct. 16 into 55 into 1000 into 7 divided by 22 divided by 280. That is, you will be getting a bracket term to be 1000 whole cube. And then it is a very simple 10 cube whole 1 by 3, that will become 10 mm. So don't get fear by seeing too much data in the calculations. You may end up getting the known value that you can take the 1 by 3rd root. But for that, you need to put pi 22 by 7. This is important. Don't keep it 3.14728, something like that. Right, so this is important, very, very important. Note on the next question. In this particular question, my dear friend, this basically grift crack theory and all we don't actually discuss for our gate examinations, and not we are not discussed basically this particular grift crack theory even for material in the material sense also. But this particular topic is very much there when you do MTech in uh, either manufacturing or in design. Even though grift crack theory is given in our material science also, right? For that you can follow NPTEL lecture. They have given, right, this particular grift crack theory. So directly you please remember whatever the concentrated stress will be there because of any crack, any material you have, any crack is there, for example. And when you just apply the load sigma, whatever the stress will be developed here at the concentrated particular point, or we call SC, that is given by 2s C divided by R 1 by 2. There is a complete lecture of 40 minutes is there, right? When you follow the Rajesh Prasad, IIT Delhi professor, he has given 40 minutes lecture on this particular proof of this particular equations. So either you can follow this one, or if you want me to explain, I will explain in a simple language, right? But for that you need to remember directly the formula, or in examination whenever you are getting this type of question, only the option is to leave the question. Do not bother. If you are not able to solve, don't think that 80 or 90 percentage population of the students will able to solve these questions, right? Only you have to remember the formula, that's it. Even I will say don't remember the formula also, because most probably will not be repeated. If repeated, luckily you will get the same question. They might be doing some R by C, C by R, or like that, changing the options. Now note on the next question which we have based on the fluctuating load machine design. Note on the data first of all. Now here based on the data, the component is being subjected to fluctuating load from sigma 1, that is minimum stress is what, 100 megapascal, to maximum stress is what, 200 megapascal. What is the other data? The material has a yield strength of basically 450 megapascal, and the material is having endurance strength of 200 megapascal. Now, by using this data, you try to understand the materials are failing at much below strength, below the yield strength in the fluctuating load. Do you change the load from static to dynamic load? your material will fail very quickly, right? They are asking what are the factor safety. So yield strength is given. Now we know the formula which connecting the dot between yield strength and endurance strength. Variable load, mean load. This line we call Soderbergh line. So we have to use Soderbergh theory. Soderbergh theory. By Soderbergh theory, like we have theories of failure for static load, like Tresca's, von Mises. Similarly, for the dynamic load also, we have different theories of failure. In fact, when the materials is subjected to both mean load as well as variable loads, because here in this question, by this data, you can get to know this material is subjected to both mean load as well as variable load. Mean stress is what? 100 plus 200 divided by 2, 150 megapascal. What is the variable load or amplitude of the load or stress? Maximum minus minimum by 2, right? So now here, when you calculate the value of what we call variable stress divided by endurance strength plus mean divided by yield strength, that is equal to 1 upon factor of safety. That is the formula corresponding to what we call here. Here kf will be multiplied. Now, here generally we used to write kd, that is equal to 1 upon kf. Kd is what? Endurance strength will be yield whatever the endurance strength given in the problem into kd. But kd here they have not given any notch sensitivity and all. So kf I am taking it as 1 because it is not given in the problem anything regarding kt or kf or any other thing about the notch sensitivity. They have not given any data. So I'm taking it as I'm taking this as 1. So here I'm writing 1 into 50 divided by 200 plus mean is value of this stress will be 150 divided by 450. That is what? 1 upon factor of safety. So here factor of safety we can write 1 upon, sorry, that will be what? That is 1 upon 4 plus 1 upon 3, that is 1 upon factor of safety. So factor of safety will be, you can write it as 12 divided by 7. 12 divided by 7 means B option should be correct. Make a note of it. Make a note of it. We also know Kf, that is a fatigue strength concentration factor, that is 1 plus Q Kt minus 1. Kt is what? Theoretical stress concentration factor. Q is what? Not sensitivity. In the problem, there was no value of means the value of Q might have, they have given it as basically, sorry, the value of Q they might have given as 0, for example. Then we can get Kf value as 1. Or it may be possible, kt value equal to 1, for example. So in that case also, once again we have kf value equal to 1. We don't know, that depends on the data is not very much clearly given this thing. Kf equal to 1 means if you want to know what is the meaning of kf equal to 1, that is the insensitive of notches. Insensitive of notches. I will explain you because we have separate question based on notch sensitivity. See that. So first of all, note on this particular question. Okay. Moving on to the next particular question. When you read this particular problem, Kf is a fatigue stress concentration factor and Kt is a theoretical stress concentration factor. Both are correlated by Q. So Kf, we know that 1 plus Q, Kt minus 1. So Q can be written as Kf minus 1 divided by Kt minus 1. So the answer should be, that answer should be obviously B, right? Answer should be exactly, has to be equal to B. But what is the meaning of Q, right? Notch sensitivity, and what do we mean by this notch sensitivity, right? That we will try to understand a little bit. Then we will move on to the next question. When Q will be equal to 0, when Q will be equal to 0, that means notch sensitivity of a component will be basically what? 0. When the notch sensitivity is 0, then what is the value of Kf? Kf will be equal to 1. Material is insensitive. Material is basically what? बाद में material is basically what? Insensitive. Material is insensitive to the notches. When Q is equal to 1, when Q is equal, see actually, when you see very carefully, when you see and when you look at the value of Kt and Kf, so actually Kf should be less than, Kt. Theoretically, whatever the stress concentration factor is there, that was predicted very high. Actually, it is not, right? But when Q is equal to 1, then Kt will be equal to what? Kf. When Kt is equal to Kf, highly sensitive to the notches. Highly, highly sensitive material. Highly sensitive to the material. Any notch, the material will gone. That is the meaning of Q equal to 1. So for our objective question, for a particularly objective question, right? In fact, when the Kt is given in the problem, take Q equal to 1. You design the material for the worst loading case, for a worst conditions. Design for the maximum stress condition. But in examination, Kt, Kf also not given. You take Q as 0. That is Kf equal to what? 1. Now, what is the general range for Kt? If I'll ask you, what is the general range? What is the general range value for Kt? Either you take any factor, that value will be varies from 0 to 1, 0 to 1, right? 0 to 1, right? So make a note of it. But Kt value can go from 0 to basically what? 3. Because when you see Kt value will depend on D by B ratio, diameter to width ratio. When this particular value is 0.1, anything here, the value will be Kt of the Kt value will be what? Approximately, when diameter to width ratio is very, very low, that means width is very, 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 very large, then you can have Kt value is equal to what? 3. Kt value will be what? 3. But as you keep on increasing the width, that depends on the data book, the Kt value will be. Again, more detailing of, if you want to understand each and everything very practically about the fluctuating load, whole chapter, then you can follow IGC lecture or IGC notes. Because not only you have to uh, read the topics, you have to understand physically also. You have to ask yourself whether you understood or not. Right? That is the meaning of understanding each and every topic. Not simply knowing the formula, solving the problem. Don't be a robot. Now, the next question will be the last question for today's session. The beach or clam shell basically marks on a filled metallic surface, they are of typically which failure? The answer is D. Of course, very difficult to answer this particular question because we know, my dear friend, if somebody will be asking me, sir, ductile failure, have you seen when we apply the tensile load? Yes, that is a cup and cone fracture. We know that cup and cone fracture happens, right? Cup and cone fracture, but when it is subjected to tensile load. And for brittle material, it will fail like this: granular transfer fracture, like a chalk piece. When you just apply the tensile load, it will fail like this. But what happens with a fatigue failure? So to explain this, let me give one diagram where you can see. Generally, when you just change your loading condition from static to dynamic load, or you just rotate your shaft, when you just start rotating your shaft, generally, then you know that when you start rotating your shaft, then point A, which is subjected to bending moment, sagging, then hogging, sagging, then hogging, sagging, then hogging, it is subjected to completely reverse bending load, and that is what highly worst dynamic load. Whenever any crack is there, I'm just drawing the diagram here. Whenever any crack is there, this is the crack. After the crack, whatever the propagation of failure will be there, failure lines, it will be like this. And away from the crack, up to certain distance, right? After that, it will be having whatever the this marking are there, whatever the markings which I have shown you here, they are having of slow growth. They are of kind of slow growth, right? They are the smooth region. You can see here. These are the smooth region lines. Smooth region. There is a no rough kind of thing. But when you just move away from a particular crack, here your location of a crack, but you can see here, very rough surfaces are there. See that. These are the final fracture zone, right? These are the rough region. What about this particular lines we call progression mark, beach mark, clamshell marks? And these are the signs of material subjected to what? Or material failed by fatigue failure, right? This material failed by fatigue load. That is a fatigue failure. Otherwise, this see, when you look at the option, you can simply eliminate whatever the beach or clamshell we never see. We see in granular fracture, cup and cone fracture, you know, uh, some other fracture. That is a ductile and brittle fracture. Nature of the ductile and brittle fracture. So definitely it has to be between C and D. Again, creep failure will not be that much damageable when you understand the name of beach and clamshell I'm talking about. So you can easily guess. But my suggestion is in examination like ISRO, when you have the choice between C and D, and you are not at all sure about D option, don't tick. Right. Otherwise, you may tick C and D, or you may get -1 instead of +3. Of course, the pattern has changed. Basically, the marking is not same as previous, but whatever the marking is there, based on that negative marking, and you will get the negative. So make sure you use so sure about the answer, then only you please answer this. Or maybe you can take a very basically what wise guessing for a particular question, so that you won't get the negative marking. Right. So these type of things, basically students will be able to get or achieve this type of question. They can answer very easily when they will be fundamentally involved in the knowledge or understanding or gaining the knowledge of fatigue failure. Like we understand theoretical, we understood formula wise. Now you might be interested how the failure will happen, and when you type it in the Google, then you might see this type of images. Right. That's why we see basically say that interest of the candidates, whether they are interested or not. When they will be start getting interest, definitely each and every question they can answer, and that is what the topper strategies and what were the topper they used to follow. Again, I'm not saying to get the full out of full marks in ISRO, but I'm saying you try to get the interest in fatigue failure, because you can see from the starting of 2015 onwards, whatever the previous year question we are discussing on machine design, most of the questions are bearing or fatigue failure. Even bearing also, the bearing failures are because of the fatigue failures. In fact, when you design any rocket launching pad, there also we consider this fatigue designing. We very much take interest in fatigue designing and the strength of a material rather than yielding failure or yielding failure, or we say plastic failure or brittle failure. This fatigue failures also we think very much deeply in designing of rockets, right? Okay, so these are all the things we have discussed regarding this 2020. Maybe next particular class, whatever we have on Thursday, we will try to see 2014 question paper, right? Thank you all.